Quantifying information. In probability and statistics, a random variable is used to describe the behavior of a random phenomenon. For our purposes, we will always be dealing with discrete random variables that take on a finite number of values. Let x be a discrete random variable whose possible values are x sub 1, x sub 2, up to x sub n. The probability that x takes on the value x sub 1 is given by p sub 1. The probability that x takes on the value x sub 2 is given by p sub 2, and so on. This assignment of probabilities is called a probability distribution of the random variable x. For a discrete random variable x, Shannon defined the amount of information received when learning that x has taken on the value x sub I to be the following: log base 2 of 1 over p sub I bits, where a bit, also referred to as a Shannon, is a binary digit whose value is 0 or 1 with equal probability. Roughly speaking, the amount of information contained in an event is inversely proportional to its probability. That is, the smaller the probability of an event, the greater its information. One very important reason a logarithm is used in Shannon's definition is to achieve additivity of information content for independent events, which is a consequence of 1. The probability of 2 or more independent events occurring is the product of their probabilities. 2. The logarithm of a product is the sum of the logarithms. To acquire an initial understanding of what information bits represent, please work through the following examples that map bits to the outcomes of a random variable. Example 1. Single coin toss. We only need one bit of information to represent the two possible outcomes of heads and tails. The value 1 could be assigned to heads, and the value 0 could be assigned to tails. Shannon's definition. Assuming the coin is fair, that is, the coin has an equal probability of 0.5 of landing on either heads or tails, Shannon's formula yields log base 2 of 1 divided by 0.5 is equal to log base 2 of 2, which is equal to 1 bit. Agreeing with our observation above. Interpretation. There is one bit of information in a fair coin toss. In other words, we say that the information content of a fair coin toss is 1 bit. Example 2. Double coin toss. We need no more than 2 bits of information to represent the 4 possible outcomes of heads heads, heads tails, tails heads, or tails tails. The 4 2-bit strings 00, 01, 10, and 11 are sufficient to represent the 4 outcomes. Shannon's definition. Assuming the coins are fair, the probability is 0.25 for any one of the 4 outcomes to occur. Shannon's formula yields log base 2 of 1 divided by 0.25, which is equal to log base 2 of 4, which is equal to 2 bits. Again, in agreement with our observation earlier. Interpretation. There are 2 bits of information in a fair double coin toss. Thus, we say the information content of a double coin toss is 2 bits. Example 3. Single die roll. To represent the 6 possible outcomes of a single 6-sided die roll, 3 bits of information will suffice. More specifically, we could make the following assignments. 001 is assigned to 1 dot on the die. 010 is assigned to 2 dots on the die. 011 to 3 dots. 100 to 4 dots, 101 to 5 dots, and 110 to 6 dots. Shannon's definition. Assuming the die is fair, That is, the die has an equal probability of landing on any one of the 6 possible sides, Shannon's formula yields log base 2 of 1 divided by 1/6, which is approximately equal to 2.6 bits. Interpretation. There are approximately 2.6 bits of information in a single roll of a fair 6-sided die. In other words, we say that the information content of a single roll of a fair 6-sided die is approximately 2.6 bits. In example 3, the reader might wonder about the 3-bit strings 000 and 111, which have gone unassigned. In a real sense, 2 bits of information are insufficient to represent the 6 possible outcomes for a die roll, while 3 bits are more than enough. This fact being reflected in our calculation of a non-whole number of bits. As we will see later, 2.6 bits can be viewed as the long-run average number of bits per die roll needed to represent a sequence of die rolls.